5.3, parabolas. Okay, let's start with knowing what the definition of a parabola is, because it is going to change a little bit with regards to what we're finding. So back when we talked about quadratic functions, we were just worried about the vertex and the axis of symmetry and that kind of thing. Now we're talking about a parabola in terms of it being part of a cone, a conic section. And so it has a little bit different definition other than just the graph of a quadratic. So a parabola is the shape of the graph we get when we have all points that are equidistant from a line and a point. So here's the vertex of our parabola right here at V. And then here's F, what we call the focus, and here's a line D called the directrix. And every point on the red parabola is the result of a point that is exactly equal distant from the focus to the directrix. So if we draw a line from the focus to the parabola and then draw a line from that point on the parabola straight to the directrix, those two lines are the same length, just like these two lines would be the same length, and these two lines would be the same length, and these two lines would be the same length. This length right here is called the focal length, the one right between the focus and the vertex, and then the same distance directly from the vertex perpendicular to the directrix. That is the focal length, and that's going to be really important when we start graphing these. So the directrix isn't really important other than it's part of the mathematical definition, and we are asked to find it on problems on this assignment. It really doesn't have a practical purpose other than just being part of that definition that makes that equidistant amount between points true. Okay, let's look at our first example using the standard equation of a vertical parabola with a vertex at 0, 0. Now, a vertex can be moved around. I don't know if you remember us doing that with H and K previously in the year. But this particular one is going to be at 0, 0. We will talk about changing that so that we can include H and K where we move the vertex. But it's still going to be different than what we learned previously. So while the stuff we're learning today does relate to the things we learned previously about quadratic functions, there are quite a few differences. So you might want to think of this as mostly being brand new content to learn about. Now there is one typo in here. So our standard equation, x squared equals 4 times p times y, is the standard equation of a vertical parabola with a vertex at 0, 0, and the distance from the focus to the vertex is called the focal length. So that's a typo that I had on my page, and I've corrected it. So if you have an old one, it would have that same typo. If you have a new copy of the notes, it would be fixed. Okay. So we're going to graph the parabola given by the equation x squared equals negative 6y. So x squared, I'm just going to rewrite it just to keep everything in line. So negative 6y. So the fact of the matter is that whatever the number is that's here, that is 4 times the focal length. Okay? So in order to find the focal length, we always have to divide by 4. Well, this one's really weird because we're taking negative 6 and dividing by 4. So negative 6 divided by 4 is negative 6/4. That reduces to negative 3/2. So that gives us our focal length here. Now, it doesn't really give us the focal length. The focal length is the absolute value. It's a distance, so it's always positive. But this does help us figure out what direction to move the point to the focus. Okay. Let me put this part back together. All right, let's start graphing some stuff here. So we've got our vertex at 0, 0 because there's no H and K in our equation yet. We'll learn more about that later. And then because it's negative, our focus is actually going to be going down. So instead of up, positive 3/2, it's going to be down, negative 3/2. So there's our focus. Then we're going to learn on the next page about how to find other points here. We can actually plug some numbers in to figure it out. But I'm going to give you this hint right now, which we'll find on the next page, and that is this distance, 6, is actually the length or the width across the parabola at the focus. So if we just go from our focus, which I graphed in blue, and we count 3 each direction for a total of 6 on each side of the axis of symmetry. Then we can use those points to graph our parabola. We can always just plug in points like we normally do. I would say, you know, plug in x values, find y values to find other points to figure out exactly how wide or specific details about our parabola. Now we are missing that detail which is important to the definition of a parabola, but not really to anything practical having to do with it. But we still have to go through those hoops and list that thing, which is this line called the directrix. So our directrix is going to be up at 1.5 or 3/2. So I'll say my directrix is at positive 3/2. My focus, so we already started with our vertex at 0, 0. That was a given because there's no h and k. You'll see the difference between that and other problems here in a second. And then we have our focus at 0, 3, negative 3/2, and that's because P right here is this number for now, since there's no h and k. P is just this number. So notice we have our axis of symmetry at 0, so that's why these numbers are both 0, but this is a distance of 3/2 away from each other, and this is going to be at negative 3/2 because of the negative in front of the 6 right here. Okay, and then our directrix was at y equals 3/2. Okay, let's keep going here. So on the next page we have this hint I was telling you about that helps us figure out how wide our parabola is. Kind of a funny name, the Latus Rectum, you know, Latin, that has been used for years to describe this part of a parabola. We're just now learning about it because it hasn't really mattered, but it's very helpful when we talk about these in terms of being conic sections. So it's a line from one side of the parabola to the other side of the parabola through the focus. Gosh, I've got so many typos on this paper. Through the focus, perpendicular to the axis of symmetry, and it has a length of 4p. And we're actually going to do absolute value, so it's a positive because lengths are always considered positive. And because it's a length of 4p, and because there's symmetry in the axis of symmetry, it's going to be 2p to the right from the focus, and then 2p to the left. So splitting that 4p distance in half so that the total length is 4p. So 2p this way, 2p that way to get the endpoints. That helps us see how wide our parabola is through the focus. Sorry for that other typo. All right. So we can also have parabolas that go horizontally. So far we just looked at vertical. And the one in particular that we looked at was actually opening downward because it had a negative. So if it had been positive, it would have opened upward, negative downward. That should be common knowledge that you've learned in other parts of this year's content. Okay, so now what has changed from the horizontal equation that we had in the vertical equation? If you can't tell offhand, let's look at it again. So we have x squared equals 4py. That one's a vertical. And now we have y squared equals 4px. This one's horizontal. So notice that the square has switched variables. So when the y is squared, our parabola will go sideways. And when the x is squared, our parabola will be up or down. One way to maybe remember that is that y equals x squared is the parabola we learned about way back with quadratics and polynomial functions, and it's a function. So if it's up or down, it's a function. It passes the vertical line test. But if y is squared instead of x being squared, that is a sideways parabola, and it fails the vertical line test. And there would be two possible answers, because if you tried finding values of y that make x true, you would get two values, a positive value and a negative value. And so I don't know if it helps that when y is squared, it's not a function and therefore it's sideways. When x is squared, it is a function and it's straight up and down. I don't know what's going to help you remember that the best, but whatever it takes, just please memorize that fact. Okay, so again, this is messed up. Focus to vertex. we're going to graph the parabola given by the equation y squared equals 12x, find the focus and directrix and the endpoints of the lattice rectum. So we're going to start by changing our 12 to a 4 times 3 times x, because now we know that that is p, right? And it's positive. So when it's positive, this is going to go to the right. Let's start with our vertex at 0, 0. And now our focus, because it's a positive 3, is going to be to the right 3. So the parabola is facing, opening to the right, because it's a positive 3. Then the directrix, just because we have to like fulfill the requirement of finding the directrix because it's mathematically important, just not practically important. Oh, that's not going to be a y equals. That's going to be a x equals -3 because it's a vertical, right? So then our focus is at positive 3, 0, and our vertex was, of course, at 0, 0, because we didn't have any extra numbers that you're going to see here in a minute, moving it around. And now, last thing we need to figure out is the lattice rectum. So to do that, we look at the number we started with, which was a 12. 4 times 3, 12, right? So that's 4p. And half of that is 6. So we're going to go from our focus and go, let's do this in color. Go up 6, 1, 2, 3, 4, 5, 6. So that point would be at 3, 6. And we'll go down. So right 3, down 6. 1, 2, 3, 4, 5, 6. So that's going to be at 3, -6, right? So that tells us exactly how wide our parabola is, and those are the endpoints that the problem has asked us to list. So the endpoints I just did in green on my graph. Now I'm going to finish sketching in my parabola by curving a graph through those endpoints, through the vertex, facing the focus. The directrix is on the other side with no real purpose other than a mathematical definition, and we're done.